Welcome you boys. We are discussing today shear force and bending moment diagram, and this is a simple supported beam is being loaded with a transverse load P and P both sides equally from the corner at a distance A from each corner, and you want to find out the shear force diagram and the bending moment diagram for this beam, which is being transversely loaded at two concentrated forces P and P from the both sides equally A distance. Now, first, before doing it, you have to find out this type of problem. You have to find out the reaction at the support. The reactions at the support is a very simple beam. It is very evident from the sketch that the reactions are P and P from the both end. One side is roller, other side is hinged, and the reactions are P and P each, and this has been found out. This has been found out by equilibrium equations, by principle of mechanics, and I have not calculated here, though it is very evident from the view that this reaction at both sides are P and P each. Now, if you want to find out the shear force diagram or the shear force, before drawing the diagram, you have to find out the shear force at distance x from the supporting, and we have to start from the left hand side. This is very convention. It is a convention that we will calculate the shear force from the left hand side. And in order to find out the shear force, we have to make it three distinct parts. Since the transverse loading is here and here, so we have to have three parts, or three segments in fact. In the segment, this is one segment. This is one segment. This is another segment, and this is the last segment. So we to find out the analysis of the segment, we have to find out the free body diagram of this segment. So we have to make a section here. Amen is a section with the distance x from the left hand side. We have to always do the analysis from the left hand side, and this is the normal convention from all shear force analysis. This is except for cantilever beam. Except for cantilever beam, for simple supported beam, we have to start from the left hand side. And we have taken a section here, x from this. The first segment is before the transverse loading is being done. So this is the point where the transverse loading has been made here. So we have to make a section here, amen here. So this is the free body diagram of the first section, first segment. And here the P is left hand side moving up, the right hand side, so we can say equilibrium equation. So the free body diagram has to be in equilibrium. So this, if you do that, the shear force here, SF here is along the X, always SF is P. From this to this, any point at from the distance to the left hand side, the shear force is P. So this is the first segment. The second segment, the free body diagram here. Why it is here? Because the loading pattern has changed after application of the load at this point. So we have made this here, the free body diagram at Amen is x is more than A and less than this here, less than L minus A. So from this to this is A and this is L minus A. So here we have done it, the free body diagram. Here the free body diagram here, this P and P cancel, so there is no balance P here. Only a moment is here. So this is a clockwise moment, this is anti-clockwise. So this is a equilibrium equation. So here SF is P minus P is equal to 0. So we have drawn, based on this, we have drawn a SF diagram here. This is the left hand side moving up. It will continuously the same P till the x, this is the x, the distance is x. So this direction is x. So along the length of the beam, if you go ahead, so up to A, the shear force is P. So when it comes to at A, so upward force is being negated by the downward force. This is the transverse downward force. So this downward force is cancelling the upward force, so this becomes 0 at this point. And if you go beyond that, so the shear force has become 0. This is evident. Up to x is equal to L minus A. This is L, this is L minus A. So here afterward, there is a P, the downward force here. So this P will keep on, the same P will be applied here, and this is the upward force, the reaction force. The reaction force negate this downward force. So this downward P and upward P become cancelled. So this is 0 here. So this is the shear force 0. The shear force upward, shear force here, this downward shear force. So this is the shear force diagram. Now this is the shear force diagram. Now we have to draw the bending moment diagram. Now we have to do a little bit of different approach for bending moment diagram, and since we know that this bending moment, differentiation of bending moment dm dx is equal to shear force. So once you do it shear force properly, so this is a very important part. If you do the shear force properly, automatically the bending moment can be drawn. This is the principle of doing it. So dm dx is equal to v. So m is equal to this dm, integral of dm is integral v dx. This means that area of the shear force diagram curve. This is the area of the shear force diagram curve. So bending moment at any point x is the area of the shear force diagram up to that point. It's a very important part. So bending moment at any point x is the shear force diagram up to that point. So if you want to draw the bending moment here, so here is bending moment here. If you draw the bending moment here, so if you calculate the area of the shear force curve, area of the curve, suppose this is a by 4, this distance is a by 4, and this is p. So a by 4 into p is the area of the curve. That is the bending moment at this point, at the distance a by 4. So again, if you a by 2 into this, so area of the curve is a by 2 into p into a by 2. So that is the area of the curve. So this is the corresponding bending moment value. And since it is linearly varying, so this will keep on increasing up to this point. So this will keep on increasing up to the point. After that, the bending moment, there is no force here. There is no balanced shear force here. The shear force is 0. So the area of the curve this bending moment is nothing but the cumulative area of the curve. So this will keep on constant value. This bending moment is constant value because there is no additional area. Now again, if you go downward, so this is the negative part of this. So you have to deduct this value from this. So here the bending moment is this value minus the area of the curve deducted from this value. So this value. Again, this area of the curve deducted this value. So corresponding values that we found out. And if you draw the curve, this is also a straight line curve because it's a negative slope. Because you just keep on reducing it, you can come down to this point. So bending moment diagram, this is another approach of finding bending moment instead of doing the moment. Instead of doing the moment equation, this is another way of doing it, and you always do what is the positive or negative moment, bending moment. Since the beam will be sagging bending moment. When you apply the load here, the tendency of the beam will be like this. This is a sagging. So this is a positive bending moment. So this is a positive bending moment. As it is to be, the load will make the sagging of the beam. And these two curves are very important because this is most vital curve, the bending moment curve, because the bending stress will be evaluated for maximum bending Maximum bending moment is the entire. This to this is the constant bending moment. This is a special case of a beam, and we call the pure bending. This portion is pure bending. There is no shear force. When there is no shear force in the beam is subjected to the pure bending. And entire length of the beam, all the points in the beam are subjected to the bending moment M. So this is one of the indications. The bending moment is the curve. Bending moment is a section by which we can find out the maximum bending moment. From the maximum bending moment, we can draw the maximum shear force. Again, one thing I want to add it, when the shear force is zero, this is one of the things. If the shear force is equal to zero, the bending moment is maximum. So this is one of the corollary of this situation. dm dx is equal to zero when m is maximum. So when the shear force is zero, the shear force is zero, bending moment is maximum. So here in the entire beam, there is no shear force there. So this portion of the beam is under pure bending.